Greetings everyone. Today we'll be talking about a paper of biomechanical modeling and pre-operative projection of a human organ using an augmented reality technique during open hepatic surgery. Our plan for this presentation will start with introduction and problematic, then proceed to related works, then proposed methodology, and then we will up to showing results, and finally we'll conclude with conclusion and future work. For our introduction, nowadays we can see a widely used techniques during open and closed surgeries of using robots or computer assisted mechanisms like humanoid robots that target organs that are hard to operate on and generally assist on the decision making of the surgeon during open surgery. For example, we can see on the right a fully exposed liver organ that is being operated on, and the liver is is an organ that is easier to operate on because when fully exposed, the surgeon can access the full organ and operate on. One of the techniques used during computer-assisted surgery is the minimally invasive surgery. This surgery is invoked using long sticks that are inserted directly into the patient's abdomen. These sticks act as the hands and actions of the surgeon through a robot that he's controlling directly. These sticks generally look something like this. They use CO2 to inflate the abdomen to make the management of the sticks a little bit easier, and it generally means a faster recovery for the patient and less pain. Our field of research was to utilize 3D visualization of the patient anatomical structures in order to help on the decision making of the surgeon while removing tumors, for example, performing cuts, or trying to locate anomalies within the specific organ. We see right here examples of visualization of two organs during one organ and the whole body of a patient during open surgery. During the research of this paper, we targeted the liver organ because it's easier to operate on, and since the liver is one of the heaviest internal organs of the human, the liver organ can be a little bit hard to work on, since for example, if a surgeon has made the decision to, for example, transfer a part of the for example, if a brother is donating to his father a part of his liver, performing the cut of the liver is very crucial to maintaining the health of the donator of the part of the organ, and therefore sometimes it could be a little bit difficult to perform this cut because there is no internal visualization of the veins or the sensitive parts within the liver to make the cut precise. We will pass on to related works. One of the papers we try to make research on is the patient-specific biomechanical modeling for guidance during minimally invasive hepatic surgery. As you can see, that was this paper methodology made the reconstruction of the organ's internal structures into a 3D model, and then they performed segmentation on the liver to determine a 3D biomechanical model of that liver. As we can see here in the final results, On E and F, we can see a generation of improved segmented map during using their algorithms to generate a 3D complete model. Our second paper related here is the silhouette-based pose estimation for deformable organs application to surgical augmented reality. This paper aimed to create a new method of the generated biomechanical model registration during the surgery. So as we can see in the image, they extracted the visible outline of the model with respect to camera's position during the operation. They performed an iterative closest point algorithm from 2D images to 3D perspective to determine contour of the organ in real time. They perform some operations to align the model directly into the field of view of the surgeon in order to get an accurate representation of the 3D model into the 3D space. As you can see, the biomechanical model was implemented using two-dimensional silhouettes. We pass on to the proposed methodology of our paper. Our proposed methodology consists of inputs and output. So for the input, we have CT scans from a patient, from the liver organ of the patient. Then we pass on to reconstruction of our geometric model, and from that geometric model we'll be generating a biomechanical model, and then we will project this biomechanical model into 3D AR space and define the algorithm needed for adding interaction to this model. Finally, we will simulate our biomechanical model and interaction with it, and the output should be an interactive 3D biomechanical model. One of the vital steps in the simulation of the model was the reconstruction of the 3D model. We used an Invisialis 3, which is an open source tool to reconstruct our model of the liver based on CT scans and MRI images. Both of these data go into the Invisialis 3 software and will return us a segmented images of the model of the liver model in our example. So after we generate our 3D model, this model will then be saved as an OBJ format and will serve as the foundation for creating our 3D biomechanical model. The next step consists of generating the biomechanical model. So in order to generate a biomechanical model, we will need to first of all generate a collision model, which will serve as how the model collides with other objects. So the collision model will utilize a set of convex primitives that hold the entire model. Each collider is composed of rigid bodies. These rigid bodies have properties, physical properties such as the mass, the drag, the gravity, and the collider model properties. These properties, or these set of convex primitives that form the collision model, will be computed in order to determine the deformation of the model. The next step is the projection of the 3D model using our chosen device, the Meta 2 AR headset. So the Meta 2 AR headset, as seen in the image, provides an SDK that is implementable directly in Unity. Some of its features include their tracking system, SLAM, There are meta camera prefab in Unity. They provide sensors data access to 3 cameras. They provide meta hands in order to access interaction with hand. They provide a meta webcam as a preview, and also provide a surface reconstruction of the area to maintain the calibration. Our final step is the simulation of the biomechanical model. In this section, there are vital 3 steps in order to simulate our biomechanical model. So as a first step, we will generate and recalculate the group of convex mesh colliders that we mentioned earlier in order to estimate the mesh colliders position. And effectively the deformation of the model slightly. The second step is the meta interaction using the deform method. This deform method will compute the deformation direction normal, so the deformation direction normal vector from the position of the hand to the position of the first interaction with our biomechanical model. We calculate a list of affected vertices and then their next velocity values, and these will be fed directly into the physics computation, which will update the rigid bodies of the convex colliders, which will then update the visual model that we see on the screen. The third step is the simulation of the model using the method fixed update, which is provided by Unity. It does physics update, which is very more frequent. This method computes the next velocity value for each affected vertex, which is dependent on different properties such as the mass, the drag, the gravity properties, the force applied, etc. Our proposed methodology of the simulation. So during the simulation, a condition should always be verified in order to update or not an interactive model. So if the velocity of the values, so if we have an interaction with the model, there should be displaced vertices update, then the mesh is subsequently updated, and the corresponding normals should be recalculated of the affected area. We have a graph here to demonstrate that. So if the simulation should start, the fixed updater will loop for each physics frame independently and check if the mesh model has changed. And the other side, we have if we have an interaction with the model, there will be a collision detected, and there will be calculation of the vector normal and the force applied, and calculate the new vex group velocities and update the mesh model. This will invoke on the other side the mesh model changes and update the mesh data to new estimated positions, then recalculate the collider model, and finally update the visual model that we can see in real time. Here are some of the results. The biomechanical, we can see the biomechanical settings in a preview. On the right, we can see the generation of the global convex collider model, which is almost as an acceptable collision model of the 3D biomechanical model. The 2 images on the bottom, we can see the projected model on the left and the interaction with the model on the right. There is a slightly small deformation that you can see because it's a little bit harder to capture during real time, but it is there. The results of the deformation, we can see the scene set up in Unity. We have our biomechanical model geometry overview. We can see inside the biomechanical model, the velocities and rigid bodies, and the interaction script that we implemented. For our results, during the test that we made, the collider was adjusted to fill the needs with having multiple colliders. This allowed the interaction with the volume model to be more precise. Furthermore, the estimated group of vertices to deform, giving a calculated velocity that attenuates over time, were executed in the fixed update method, like we mentioned earlier, and consistently evaluate a new displaced position until the velocity values approximately nullify. This marks the end of the deform action and originated from the hand interaction. For conclusion and future work, in this paper, new augmented reality approach is proposed in order to simulate the reconstructed model of the human liver organ. Given a set of pre-operative data such as CT and MRI images, a new methodology is established to generate and manipulate the biomechanical model. The results offered by the proposed approach are convenient, representing the efficient tool to help doctors during open hepatic surgery. Nevertheless, the accuracy of the simulation depends on the number of density of mesh colliders representing the surface of the biomechanical model, and therefore the precisionness of the interaction of the model. Thus, the future works will be focused mainly on the development of improved algorithms to manipulate the generated biomechanical model. These are some references for the related work, and thank you for your attention.